So it is what we are going to do, just in the middle paragraph. I'll put in memory of him.
Okay.
Hoping that maybe a wonder will happen. Oh, who we are and what are we doing? Oh, by the way, I've heard feedback that some of you suggest to set up the presentation not on coming Thursday, but 1 week later. Are you like impatient, rushing to present this Thursday, or you would love next Thursday for more preparation time?
I mean, I have to grade like hundreds of tests
This
by
Thursday or
like
next
Wednesday
Thursday?
night, so I would be okay with pushing it back.
I'll be fine with it.
Huh?
I have a lot of lab reports to get done.
Is there anyone against pushing it to next Thursday? Anyone for pushing it to next Thursday? You don't care.
I don't care.
Okay, so if you started preparing it, it's great, and it just gives you more time to prepare, because this Wednesday I will be at the lab and instruct. Next Wednesday it's physically not possible. I will be in the airplane. You do not, even if I would like to do it online, the connection will be not stable. So I'll just, you've got some materials, right? In the email, and I'll try to cover as much as possible in coming Wednesday. Good. What are we going to do? I'm spoiled and tempted by the slides. It is much more energizing when there are no projectors and you need to write everything from scratch on each lecture. It's more organized and much less garbage. And now I can inherit garbage from previous years. So we are in the middle of the third chapter. Our goal is to describe systems of real molecules, to compute observables, and we already have the software and hardware, but we want to get an idea how it works and what are the principles, why it works. Because the efficient methodology, density functional theory, is not, was not accepted by everyone later, and still, right now, there are more advanced methods which we may use later, but as a workhorse for intermediate preliminary results, there is nothing better than DFT. But if you use it and publish it, you need to justify why it works, why you want to do it. So we are going in much details of the principles behind the DFT. Last week was useless completely. We just got through two theorems. One, that a density allows to reconstruct external potential, basically the potential created by ions. And second, that if you know density, you know the minimal correct total energy. Next two lectures, thank you for agreeing to push your presentations 1 week later. Then we will basically finish most important theory parts this week. So today and coming Thursday, we will be doing something much more helpful and useful. We will go into practical aspects of density functional theory. So theorems tell that very pleasant things, that if one can construct density, which is very much simpler function, one can find total energy, which is the goal. Main observable is total energy for chemical stability of a molecule. But theorems do not tell how to find energy, how to construct density, what is the procedure. So we split the journey into this practical one on 2 or 3 sections. three. First, it will be the thing that will inspire your imagination. That if you were not reading literature in PhD, you cannot imagine and predict right now. You already know that this area of knowledge sometimes is counterintuitive and surprising for students. Now we will again go into imaginary world that doesn't exist, auxiliary world, but helps a lot to get right answer about right molecules. We will get into the world that does have ions. Remember, in Thomas Fermi's theory, we were talking about the world that has only electrons and no ions, and no electron-electron interaction. Now we will be super advanced. We will go into auxiliary world that does have ions that attract electrons, many electrons, but electrons do not interact with each other. And if we get an idea about this world, we will later, very soon, we will be able to describe our true world. So we will get concept of so-called correlation, auxiliary world, and then procedure how to construct density if we know orbitals. And of course, we need to introduce orbital. So about this paragraph, and on Thursday, we will try our best to set up algorithm similar to Hartree-Fock algorithm, but the density function algorithm that allows to convert initial geometry of a molecule, position of atoms, into total energy through some auxiliary concepts. Make sense? Okay, and if I will not be deriving everything but showing slides, we have a little more time than we need. Of course, we can quickly do everything in 10 minutes and depart, or we can invest time in just discussing our plans for the rest of the semester. So, very soon after completing your presentations on past skills, we need to put pedal to the metal for doing projects. And completion of projects will be very much standardized. It's like do 1, do 2, do 3 protocol. But selection of projects which you want to pursue is your creativity, your imagination. So it's better if you start thinking about it ahead of time. So I'm going, before I go to this material, which will excite you if you have analytical type of thinking, and will be boring if you think more practical things. I'll postpone it by about 10 minutes and start speaking a little bit about possible practical problems for mini research projects that we are going to complete by the end of semester. And I'll try to return to it again and again before we start actual research. So I am going to request, mandate, suggest any project to anyone. You can select what you want to research yourself, but there are just some ideas. So we are on number 20. We'll get a full chart next Thursday. Then on Tuesday, I'll probably pop up through internet. I will be in different cities. And then on Thursday, you present on how to run Rust and how to find observables. And you don't know approximately what each of you is going to present, right? So let's concentrate. I will give you heads up what will be important didactic information. Nowadays, just to give you opportunities and start thinking in different directions. So the previous years, so here is the list from previous years, and here are some subjects that can be very new. And I will also show some figures of and Reddit scratches. Generally, the skills that you are going to accumulate will allow you to do almost anything in modern science, in chemistry, physical chemistry. But there are generally two directions. They sometimes overlap, but two directions. One is photophysics, another is photochemistry. Why photo? Because without photoexcitation, everything is boring. Sometimes you can replace photoexcitation to thermal, but okay. Physics and chemistry, it's too general. Whatever molecule can be placed in the aggressive chemical environment. One of the simplest aggressive chemical is hydrogen peroxide that will etch almost everything. And it is really nice to see molecular dynamics of etching. You can look for photophysics, meaning like just properties of ability to absorb light, to transfer charge of different nanostructures of different semiconductor materials used for photovoltaics or electronic applications. This would be very interesting. And you can select like contacts of metal and semiconductor nanoparticles. This could be interesting thing. The stuff that we are going to cover in the lab will be sufficient to model not just pair of reactants converting into product, but to simulate like liquid phase. If you do simulation cell with modern pair reactants, you can one of the projects that was done in the past but can be something similar can be continued is mix of fuel and oxidizer and looking for ignition and combustion, probably like several combustion reactions will. Enough. Too long list, of course. So some of you are exposed to perovskites and they are in some of our homeworks. I apologize that I didn't give you pleasure to do homework this weekend. It was too much things with the conference, but I'll try to generate it and then share later. But if you build perovskite models, you can investigate it's in different, same composition but different shape and size. So different periodicity bulk, two-dimensional slabs, where you can deposit different surface agents, different capping, passivating molecules, or you can deposit there a dye molecule that will pull either whole or electron to set up dye-sensitized source. So you can try to do an interface of three component materials, like the slab of perovskite that absorbs light, and then electron acceptor and hole acceptor on different sides. Like you may imagine hole acceptor accepting molecule or spirometer, and put a little cluster of titanium dioxide on other side. And then upon photoexcitation, there will be charge transfer on both sides, electron to one, hole to another. Nanowires, even if you do not deposit anything to them, they are very promising materials, and their properties. There are a lot of fun properties that are not observed in any other shapes and structurization. Austin is not here, but you can dope either bulk or cluster with transition metal doping and make it luminescent center in the perovskite. But anyone else can follow this stuff. Braden is not here, but you can investigate carbon nanotubes by putting their adsorbents that also are photoemission centers. But because carbon nanotubes are chiral, you can select one side, one direction of chirality, opposite direction of chirality, and see how they affect the optical properties. So with little effort, one can reconstruct this vast simulation with our ability to see three components of transition diagram. Catalysts. You guys program much more together than myself. Well, catalysts, but catalysts can be homogeneous and heterogeneous. So it could be just dissolved catalytic agents, and they can be like molecules, relatively small. For example, it could be metal-organic complexes where we react and blend and then depart. Or it could be heterogeneous catalysts when like metal clusters or just some active surfaces, which is a subject of physics surface, where the reactant blend makes temporary bond, meets another reactant, and then departs. Okay. I'm just trying to launch your imagination. Things can be done. And there are metal-organic complexes where you can select the left and right chirality. They're not equal, and sometimes they promote reactions giving raise to either one or another isomer in the product. This also could be an interesting subject to pursue. So, perovskite, Hall acceptor, electron acceptor. Work of perovskites and looks forward to return his primary research interest of metal-organic stuff. What you can do, it will be competitive research, but it is like on the edge between educational and competitive. Some simple standard metal-organic compounds like B-pyridine, and then bombarded with water molecules under condition that oxidation and multiplicity is artificially modified. So it may, if one sets up it in a right condition, like if one creates highly catalytic metal, it will highly charged. It will be able to promote redox reactions of something simple like water. So it is very, very possible to do it. Or simple thing can be done if you deposit metal cluster, also bombarded with something. Okay, doping. Alisa is not here, but if some of you are thinking of biochemical or computational biochemical career, or just have interests, the simplest thing you can explore toxicity, how the cell membrane is reacting on the interface with inorganic substances, which can be a surface or dissolved metal ions or some chemicals. And, if one takes a little closer and bring a very narrow part of it, it can be modeled explicitly. So this is for chiral dichroism of carbon nanotubes. So for different chiralities, the dipoles of deposited emitters are setting up helicity in different ways, and they will give rise to different interaction with shock wave in carbon nanotube. I think it is boring for chemists. Interface of silver and silicon quantum dots or nanoclusters, you just set up minimized thing and explore when they are in contact with chemical bond between them, or when they are interacting through vacuum, and explore availability of charge transfer states. Church states are needed for photovoltaic, and presence of a bond gives allows or disallows. Enough. So Walter Kohn is not with us anymore. He passed away a little bit more than a year ago, and last year, Senegal conference, one of his apprentices, who is a letter B in the functional PBE, here in the book, was given his impressions about being a student of Walter Kohn. He was telling me, I don't know, he probably needed his best student, I was his worst student. And Kieran was telling fun stories. So this is a gentleman who designed the protocol how to find observables based on position of atoms through these theorems of density function. And he introduced the concept of auxiliary orbitals. So in the community of density function theory, we will not use the word molecular orbitals. We will tell on orbitals, on Shang orbitals, because they are not true orbitals that you can observe. They are from other world, from auxiliary world. Although they help to understand something in the real world. So, if you think you are tired and you cannot remember much, just remember this. So, this is energy, this is density, square brackets means function. Done. This is a summary of what we do. And those are two theorems that we covered on two previous meetings, right? So from density you can get external potential, and from density you can get minimal, absolute minimum, best reliable total energy. So we are going to get several concepts which will allow us to establish protocol for implementing the energy out of density. So concepts are functional derivative, the universe where electrons do not interact, auxiliary universe. So we need to be able to move to this auxiliary universe and then return. And a way how to construct density out of orbitals. We kind of know it intuitively, but we need a little bit more background for this idea. Orbitals and needle. We can go very quickly in session. So the first concept that we need is functional derivative. We need to make connection between energy and potential. When we are residing under paradigm of standard quantum theory, we are finding any expectation value as how? What's the right word?
The angle brackets?
Yes. Any synonyms?
To expectation value, or like, I guess.
Yeah, like whatever. Direct product, direct notation, bra times cat with operator. Bra, cat, and operator. If we know that our operator is diagonal in selected basis, which is very true for coordinate Cartesian basis and operator of potential energy. Then this Dirac notation can be reformulated as the potential times density, which is wave function conjugate to itself, and integration. Right? This is simpler expression compared to bracket notation. Okay? You don't object. It's H standard. Now, there will be simple things. Even not being in sharpest condition, I would be able to write it down, but since it is written, I'll just carry you through. So it's very simple, few symbols that you already see, but please be alert. There will be a little counterintuitive thing. So in your standard calculus, you have functions and you have derivatives, right? And you do have increment of function, increment of argument, and their ratio is the definition of derivative, right? df over dx, in the limit dx goes to 0, is definition of derivative. Is there a way to generalize this concept? So what if we consider this stuff before the integration? If we submerge the density under the sign of derivative. So we are looking how the contribution to total energy will change under a given potential if you slightly modify the density. Then there should be, we should introduce symbol delta if you remove integration. And if you are looking for infinitesimal change, not of one-dimensional variable, but a function, then there is a convention to use this delta symbol. So the response of change of total energy to change in the density. This is multidimensional things. It means density changes a little bit everywhere in each point in space. And we right? And now no one forbids us to break the story by dividing both sides on the infinitesimal change of density, right? So divide left and right by this delta rho root density. I didn't offend formal logic anyway, or you didn't quote me on this, right? No objections. The only thing I need to add is to put a limit. This change of density goes to 0. So this opens new horizons for us. So if we know how the total energy responds to the modification of the density, we do have the potential. Okay? And if it would be one-dimensional variable, this will be derivative. But since it is a function, it is a functional derivative. So now you can go to get mathematical degree in theory of functions.
All those years just gone. I spent 3 years of my life getting a mathematics degree when all I needed was this.
So, and it is same as in calculus, integration and differentiation. You can go 2 ways. Functional derivative gives you potential, or integration of potential gives you the energy. Right? So at least for Right now, we do not care about interaction with electrons. We assume that we have density, we assume that we have potential exerted by ions, and we have procedure to get the contribution to the total energy. We didn't consider yet electron-electron interaction and kinetic energy. How to solve problem? Assume that it doesn't exist. So with this logic, we will assume that there is a world where electron-electron interaction doesn't exist. And then you try to justify it. So interaction with ions, interaction electrons to electrons, and kinetic energy. And for kinetic energy, we took CHEM1. We know that you can do one electron Schrödinger equation. You can set up operator of kinetic energy, and it is more or less standard procedure if we if you're not pure enough to stand in density functional paradigm all the time, and temporarily we jump back into orbital concept, at least for kinetic energy. There are some people who practice orbital-free density functional theory, but they are in minority. The way that we are going to do is more standard and practically helpful. Most of the codes that people use for practical things are use the concept of Kohn-Sham orbitals. What did I say? Electrons, ions, kinetic. Electrons remove, ions are here, kinetic needs to be added. Right? And then we have total energy. Oh, yeah. Electron, ions, kinetic. And you know from your tenure, from your curricular, from your academic, didactic, from your scholarship of Hartree-Fock, that for electron-electron interaction you have direct repulsion and you have exchange that stabilizes. There is one more thing that is missing in Hartree-Fock. There is a so-called effect of electron correlation, which I do not understand. London, you are sitting close to volunteers, please. Can you come up? I will explain a concept that I do not understand. Do not sit.
Okay.
There was no.
You have to do a back flip off the chair.
I feel like it's a good way to get hurt.
So the chair is ion, London is electron, and I'm electron. Let's walk around.
Where's your angular momentum?
So, no, stop. I do not want to collide with him. Maybe he doesn't want to collide with me. Right? So even if there is an attraction center, we want to use it. But we will be on different sides of a chair. So our motion, even if we are distributed objects, is correlated. He's there, I'm here, on opposite. Okay, thank you for the help. It is maximal amount of knowledge that I can tell about electron correlation.
Shoot.
So if we do have positions of London and myself, and there is a density, one can assume it as like combined of density of one object and another one. But what if they are not equal? The difference from between the total energy computed from true multi-electron density and the density composed of this uncorrelated components is correlation energy. This is a finer effect. It is finer compared to exchange, but it is next order of correction. And there are advanced wave function based theories that explicitly take it into account, but Hartree-Fock doesn't include it at all. But DFT can do a trick. without going into the deep derivation of this effect, it can set up a type of function that takes into account this correlation. Therefore, later, when we will tell about the functionals, they're often called exchange correlation function. Because for direct Coulomb, it is trivial, everyone knows how things repel, but for exchange and correlation and their mutual influence on converting density into energy is more art than science. So when you run Gaussian, you select your function, P through or PVE or something else. You select your exchange correlation function. It's a silly example. If objects are independent and you do three-dimensional picture, it takes all space. If they correlated, it can be more exotic distribution. I believe in this picture 3 years ago, not anymore. So, independent electrons. The best way to solve problem is assume that it doesn't exist. So we should assume that electron interaction doesn't exist. The theorems, since I went through the slides last time 2 years ago, it will be a surprise for me to see what is next. I'll try to express what I think, and then you will check whether I was right or not. So the theorems tell that if you know the density, you can, it does determine the minimal correct total energy. But theorem doesn't tell the procedure. Right? Intuitively, we know that there is interaction with ions and electron-electron interaction. But based on theorems do not tell which term is leading, which is more important. What gives bigger contribution to total energy? Interaction with ions or electron-electron interaction? And proportion of which is heavier is also not set up in theorems. So one can try a mathematical trick. So you have nuclear to electron plus electron to electron. Assume that we have a parameter lambda, and we multiply the contribution from interaction with nucleus by this parameter and by interaction with electrons with 1 minus this parameter. Maybe it's opposite, but the idea is the same. So summation of lambda and 1 minus lambda is 100%. But if you have like a pulling button, a knob that you can turn between 0 and 1, you change the relative weights of electron-electron interaction and the electron to nuclear interaction. You can set up that their summation is equal constant, so we do not violate theorems, and we just play the internal mechanism. We know that in the true universe, both interactions exist. But you can design artificial universe where the interaction with electrons is lighter, and then not existing, and interaction with ions is heavier, and gives the all energy. Do you like it? Formally, we do not violate theorems, although we are doing something terrible. So there is no 1 minus lambda. We just I unintentionally lied in a little detail. Not words, all words were correct. You don't multiply by 1 minus lambda. You just put parameter lambda, and then here it is the electron to nuclear interaction is parameterized by this parameter. So you change the functional form of connection between density and energy of interaction between ions and electrons. So if you go from parameter lambda value equals 1, and here when it is 1, it will be true world, and as you go from 1 to 0, you need to change the potential, the interaction between these ions, make it such heavier so that if you reconstruct the total energy, if you go to the universe where parameter lambda equals 0, we are not in a real world. It is an artificial world that doesn't have electron-electron interaction. But in this artificial world, we can get the same total energy as in the real world. So if we establish a procedure that will allow to go to this artificial world and then return, based on theorems, we still will be getting true total energy, which is our main observable, which is our goal. So right now we need to set up to find the potential which will correspond to the universe without electron interaction, but we need that it will give the correct total energy. Okay, so out of 3 problems, we get rid of 1. We do not have electron interaction anymore. We have general idea how to treat interactions with ions, and the only thing that we need to deal with is kinetic energy. Right? What is kinetic energy?
The energy of motion.
Sure, but mathematically. Operator of kinetic energy, how does it work?
P squared over 2m.
Yes. And how do you cast it in form of derivatives?
H bar squared
Minus h bar squared over 2m. Yeah, and then gradient squared. Or yeah, if you're doing 1 dimension,
Yes.
that's just that.
So because P is minus I h bar. But it is for 1 dimension.
Yeah.
Or the gradient for 3 dimensions. But we yet have multi-dimensional object. So it prompts us that we need to go from multi-dimensional to reduce number of dimensions. So suppose that we do have the total energy. And we know how to construct kinetic energy based on, suppose that we know how to construct total energy based on the density. Then the potential of interacting with ions, and note that it is not a true interaction with ions, it is interaction with ions in the auxiliary universe, is subtraction of total energy minus kinetic. in this auxiliary universe. And if we do need the one-dimensional potential that acts on one element, if you need potential, not the energy, but potential, we do functional derivative. So we subtract total energy minus kinetic energy and take functional derivative. And this will be the potential. Why? This is, I don't know, is it hardest or simplest, but it is most important practical step. So in order to find kinetic energy later, to set up procedures that will give us all three components, we need an operator. And we need an operator that will fit into this system, into this in our logical construction. So it is a potential from auxiliary world, not true world, auxiliary world. But if we know kinetic energy and total energy, we just set it up as functional derivative. Now we do have potential. And if you do have potential, we can do some little things on the language of Schrödinger equation. So do not expect a linear logic. We again will go into self-consistency cycle. So if we forget to define something, we assume that it's already found, and then we'll get it in the next iteration. Later, the kinetic energy will come as a feedback from previous iteration. Now, suppose that we know this thing, then by formal definition of functional derivative, we are getting potential. Okay? If you love wave functions, you should become happy now. Well, sometimes you never get happy when discussing formulas, but if you want to become happy looking at formulas, it's time. So we set on previous slides, we did set up a procedure that allows to construct a potential, not true potential, potential from auxiliary world, where electrons do not interact with each other. Therefore, here we have Schrödinger equation for all electrons in the system, in the outer world. And there is no electron-electron interaction, which is really great. Electron interaction is correct for true systems, but it's pain in the part of body for any calculations. But here we just get rid of it. So there is kinetic energy operator and potential acting on multi-electron wave function. If someone would tell us that we need to solve this equation at the beginning of the course, we'll complete the course in 2 weeks rather than 4 months. This even with many independent variables, without electron-electron interaction, it's not. Your background allows to solve. We will do it. So, if electrons do not interact, then positions of each electron are independent variables. So we can practice separation of variables trick from a course that some of you are taking in physics. Partial derivatives, methods of mathematical physics. I'm sure you practiced separation of variables.
Not yet in that
in
course,
this
but
class.
we have seen it in other courses
Yeah.
before.
Okay,
Like 3
let's practice it now. Not in the rigorous way, but just sketch the path. So I will be super convincing. If you have many electrons, you have capital, big Hamiltonian. If you formulate energy operator for each separate electron, it will be small, lowercase Hamiltonian. Convincing? And if you add together partial contributions, these little Hamiltonians for each electron, you'll get that big Hamiltonian for all electrons. So if there is no interaction, if the variables are independent, you can split your differential operator in your partial derivatives differential equation into summation of operators acting on each variable. Try to object now or stay silent forever. Okay, no one objecting. Then, so right now it is a key point, no return point. If you accept next step, if you would leave before 1965, you would just sell this idea for Nobel Prize. So instead of one multi-electron Schrödinger equation for this operator, you can equivalently solve little Schrödinger equation for each of these little operators. Okay? So kinetic energy, you already dictated me what it is. Potential energy is a functional derivative of this from auxiliary warm, total energy minus total kinetic. And so each little Hamiltonian kinetic plus potential acting on the orbital for electron number 1, energy for electron number 1, orbital for electron number 1. So it is system of one electron Schrödinger equations for each electron. Okay? No objections. Question: how these electrons differ from each other? Is there any difference in these electrons if they all have the same definition of kinetic energy, and if they all feel the same potential, and if they interact? Question once again, is there a difference between Schrödinger equation for electron number 1, electron number 2, electron number 3?
No.
No. So we have whatever 100 electrons, 100 sets of orbitals, but they will be the same because these electrons do not interact. I need to record it. So first, from multi-electron Schrödinger equation, we go to, from one multi-electron Schrödinger equation, we go to many one-electron Schrödinger equations. And second, each of these one-electron Schrödinger equations are the same due to lack of electron-electron interaction. If you are taking notes, you probably have recorded it. Even if you are not taking notes, try to record it. This is not recorded right now, and do not hesitate to write it down in your papers. Although it was published, everyone knows it. Walter Kohn got Nobel Prize for it. Write it down. Write it down, and do not hesitate to reconstruct it in your methodology, because you still need to justify that your methods do work, and this is a good thing. So you reduce your problem to a system of non-interacting electrons, each of which obey the same one-electron Schrödinger equation. Try to write it maybe by your own words. Let me know if you need a pen, if you never planned to do notes. I have 4. Anyone needs a pen? Just give me time to complete writing. So, in the literature, one often uses the Greek letter theta lowercase for these orbitals, just to underline the fact that typically we use lower letter phi, Greek phi, right? Here one uses different letter to highlight that those are not from our world. They are artificial things. And what you did last time on Wednesday, and what I missed to ask you to do as a homework, orbitals. Those are not true orbitals. Those are these orbitals from auxiliary world. So when you plot orbitals from DFT, par charge files, those are theta, Kohn-Sham orbitals. Good. Now, we are building a very beautiful construction of how to find total energy, but we are not done. Remember, since we are going to practice self-consistency, we have left some items missing, just assuming that we know them, but we do not know them yet. Right? Standard thing. So what we are missing, and it will be the last thing for today, not the last thing in the course but for today. So we need one more intellectual effort. The construction of true world density out of auxiliary world orbitals. Construct true world density out of auxiliary world orbitals. First, how do you construct multi-electron wave function? This I'm practicing laziness in setting up feedbacks, exams and quizzes, but if one would like to set them up in the course, it will be excellent question for a quiz. So it is something that you may consider to as a take-home message from previous month. So how to construct multi-electron wave function out of orbitals.
Use the slider determinant.
Exactly. Full credit for a quiz. You remember, right? So the determinant is a protocol how to construct multi-electron wave function out of one electron wave. So I just need to read it from the screen. So if you have orbitals for first electron, second electron, and all as many orbitals as many of them are occupied. All occupied electrons, first, second, third, orbital electron 1, 2, 3, one right determinants, and it will be multi-electron wave function. How to find density out of wave function?
Multiply it by its complex conjugate.
You are terribly right.
But you forgot the integration.
If you do not integrate it, and you have as many electrons, n equals 100, you have 100-dimensional, or 3 times n dimensional density, multi-electron density.
Or 300 integrals.
Yes.
300 times the phone.
If we want to normalize this multi-electron wave function, we need to integrate it 3n times, right? Then we will get number, which is likely give us n capital, number of electrons, if orbitals were good orbitals, non-confronting. I'll write it down before going forward. Here. Without integration, we get what? Multi-dimensional density. 3n dim then. Three-dimensional density. If we integrate it 3n times, we will get number, normalization. The truth typically is between borders. So we need to integrate less than 3n and more than 0 times. Okay? How many times should we integrate? If you need one electron density. If you need to project multi-electron density onto one dimension.
Just
How many times we need to integrate?
Once.
Huh?
Once.
Ah. So if we integrate 3n times, 3n times, we get zero-dimensional number, scalar. If we integrate 0 times, we get 3n dimensional density.
integrate n times?
If we integrate n times,
No.
we will get
2n,
2n
yeah.
dimensional. And we need just 3-dimensional.
Yeah. So 3n minus 3.
Yes. If you do 3n minus 3 times integration, we will get 3-dimensional density. Make sense? So we need to integrate over all but one positions of electrons. All but one. Oh, I had another empty thing. Right. All but one. What do we do if we do not have enough steam to discuss general multidimensional things? We do practical discussion of minimum multidimensional things. Like instead of n, you tell n equals 2 and see general trends. So that's n equals 2. One we need to see. So multi-electron wave function of R1, R2 will be square root of 2 theta 1 R1 theta 2 R2 theta 1 R2 theta 2 R1. Also good question for us. I'm just making notes for future years. No objections. For density, so what is capital? Rho capital of R1, R2, it should be psi star R1, R2, psi without star R1, R2. Correct? So psi star R1, R2. Am I so silly that I will just calligraphically write? Probably yes. Just practice patience. Star. 1, 2, minus star 2 star. So we need to take these two things, multiply, and put it, and then if we need dependence rho of R1, we need to integrate this thing over dr2 and see what happens. The result will be very simple. You can guess it right away, but this will be a proof. So I'll do it on the board, but please try to practice it. See what. You have something to write this?
Yeah.
Okay. So it will expand over, take some space, but you will be surprised, and then you will never forget the result. I should admit I was showing the result. If you just scratch through your memory, you will recall it. But if you derive, you will see the beauty. So we have two factors. Each factor consists of two terms. So if you multiply these two factors, the total number of terms will be 2 times 2. 4 terms in the result. So we should carefully develop 4 terms. Each of terms will contain product of 4 ordinals. And then we need to integrate over variable R2, each of 4 terms. So we are like Jeep 4x4. 4 terms with 4 factors. So I'm underlining the terms that depend on R2. This, 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 and this. Please announce answers if you are ahead. Did you?
1/2 of like the first density of R. Well, okay, so both the densities are functions of R1. So it's 1/2 like the first density plus the second density.
Yes. Did you get it? So you have 4 by 4 for terms with 4 factors, and you do know that orbitals must obey orthogonality. So if you have theta 2 and theta 2, if integrated orbitals are the same, this integration of these two terms will go to 1, and we have only these two terms left. Now here, two things that depend on R2 have different indices. So it's delta of 2, 1, right? So this term will disappear. Delta 1, 2. Here you do have R2 is an argument of theta 1 and theta 2. They also are orthogonal. So delta 2, 1, right? So the cross terms disappear. And here you have R2 in theta 1 and theta 1. So it will, due to normalization, this will be 1. So we have product of these two stuff and these two things. And we have 1/2 overall factor because of square root of 2 squared, right? Agree? So you should get, according to London, 1/2 theta 1 of R1 absolute value squared plus theta 2 R1 absolute value squared. Okay? We are under pressure or above the support of the theorems. And theorems tell that the little technical details may vary. We can be in the wrong or right world, but total energy and total density are not changing. And based on these theorems, although these densities, these orbitals, are from auxiliary world, when we process them this way, they give us density for a true world. So when we practice this stuff, we are getting rho total density of all electrons as one-dimensional function. So this is true. True. This is auxiliary. Okay? Well, years ago, but you taught all these things. Integrate over 1, the Slater determinant, practicing the orthogonality, right? You recognize these equations. Multiplication of 2 multi-electron stuff, 4 by 4, with delta functions going to either 1 or 2. And after practicing this exercise, you are Probably we get rid of number if you take up and down, but if you add together the densities of independent electrons from auxiliary world, we are able to reconstruct density 1 parameterized by one position or three-dimensional Cartesian density of all electrons in a true world. And this protocol, this procedure, will be used to close the loop. When we were setting up the potential, now again I'm not telling you things, we already covered it. Most important thing was the functional derivative. When we got potential as the functional derivative of total energy minus kinetic. Right? But to get the kinetic energy, we need the total density. And now we do have total density. We plug it into definition of potential, but the potential will be used to find the orbitals in the auxiliary world. Okay? So we are going to build the self-consistent cycle where this potential, density, and kinetic energy are going from one to another and form the closed loop. Through iterations, we get convergence. So the total energy at each iteration stops changing. This is general idea that we just sense in the air, but we will go through it in details next time. I hope very much that if I click next page, we will get to declaration of. Yes, yes. So meeting is done. Thanks much for your questions and for your effort. See you on lab 5 p.m. Wednesday if you are for class only, and you are invited to the research meeting at 4 with your results section for your papers if you do research.